This is a short video on gears. Electric motors are effective actuators. They are fast and inexpensive and easy to control. One of their downsides is that they often produce high speed and low torque, and so gear reduction is required. And gear reduction introduces backlash and other undesirable traits. So we're going to look quickly at gear reduction. Here are several different types of gears, and you can have a single stage gear reduction like this. Further gear reduction, a higher reduction of speed can be accomplished through multiple stages. So if we define the gear reduction R as the ratio of the input speed to the ratio of the output speed. So we have gear A and gear B. Then we can compute it according to the number of teeth on the gears. So the way you can see that is if we define this velocity here, this linear velocity, V, it's the speed at the pitch radius of gear A and the speed at the pitch radius of gear B. So velocity is equal to that radius of A times omega A. And since these gears aren't slipping, that's also equal to the radius of B times omega B. So we find out that gear ratio is equal to omega A, or is defined as omega A over omega B, which is also equal to the pitch radius of B divided by the pitch radius of A. And now the number of teeth on a gear is proportional to the pitch radius. So the gear ratio can be directly computed for this simple or one-stage gear train by the number of teeth on gear B, the ratio of the number of teeth on B to the number of teeth on A. Alright. You can also have a gear train, and so we'd have gears A, B, and C, and this can be used to reverse the direction of the output gear, or to change the spacing between the input and the output shaft. So in that case we have A, B, and C. And again, the velocity RA omega A is equal to RB omega B. And the speed, the linear speed of B at the pitch radius is equal to the speed of C. So that's equal to RC omega C. So the gear ratio for this gear train, again, is defined as the input speed divided by the output speed. And that is just equal to RC over RA, the pitch radius of C over the pitch radius of A. And again, that's equivalent to the ratio of the number of teeth on C to the number of teeth on A. So the gear B is called an idler gear because it doesn't have any effect on the gear ratio. And then the final gearing system we'll look at is a compound gear train. So here we again have an input shaft and an output shaft, but then there's an intermediate shaft that has gears of two different sizes on it, two different radii between B and C. So I will duplicate this drawing here. So in that case we have A and B, and then on the same shaft as A, or I'm sorry, the same shaft as B is this gear C. And then interfacing with gear C is D. So we have A, B, C, and D. Alright. The difference here is that this velocity, the linear velocity on A and B, is not the same as the velocity on C and D. So we'll call this V1 and V2. So V1 is RA omega A, just like we saw before, and since it's A and B don't slip, then that's equal to RB omega B. And V2 is equal to RC omega C, which is equivalent to RD omega D. Now, one thing we know about these angular velocities, I'll go back to the other figure, maybe it's clearer. The angular velocity of B is equal to the angular velocity of C because they share a shaft. So omega B equals omega C. And so we get that RA omega A, this V1, is equal to RB times RD over RC omega D. So just substituting, well, solving for omega C in this equation, and then substituting it into this equation, we get RB times that. And so our gear ratio for this compound gear train is defined as the speed of the input divided by the speed of the output, so the ratio between the input and output speeds, which from this equation here we find is RB over RA times RD over RC and again this ratio here, these two ratios, this ratio is equivalent to the number of teeth on B to the number of teeth on A, and this ratio is equivalent to the ratio of teeth on D to teeth on C. So for a compound gear train, the ratio, that gear in the middle, these gears in the middle aren't idler gears. They do have an effect on the gear ratio. So here I wrote it with a lowercase n instead of an uppercase n. And I called it G instead of R. Anyway, the gear ratio is number of teeth on B over teeth on A times teeth on D over teeth on C. And in the next video, we will look at the characteristics of different electric motors.